Come on, my dears, let us proceed further in chapter number 2. Please kindly read the statement of illustration number 2. Come on, read it. Look, just recall first equation of rotational motion performed about stationary axis of rotation with constant angular acceleration. Remember that equation? Omega equals to omega 0 plus alpha t. Fine. Omega equals to omega 0 plus alpha into t. Fine. What is omega 0? Initial angular speed. What is omega? Final angular speed. What is alpha? Constant angular acceleration. What is t? Given time. Now, last time we had obtained one relationship between magnitudes of linear velocity and angular velocity. Remembered? That relation was v equals to r omega. When you write here initial velocity, say v0, then here you must write initial angular velocity, that is omega 0. Find out omega from here, it will be v upon r. So, omega is v upon r. What is omega 0? It is v0 upon r. Omega 0 is v0 upon r plus alpha into t. Find out alpha into t, transfer this term, from plus it will become minus. Take LCM, r is there in the denominator, v minus v0 in the numerator, and this t you can transfer in the denominator just to find out alpha. All the values are given except alpha. Come on, final velocity, you are given one mini train and that mini train stops after some time. Because it stops, final velocity must have become 0. So, this final velocity is 0 minus, what is this? Initial velocity. Are you given 18 kilometer per hour? No, kilometer per hour will not do. You must convert it into meter per second. How? You know, just multiply by 5, divide by 18. Kilometer per hour to meter per second, come on, multiply by 5, divide by 18, multiply by 5, divide by 18. What about radius of wheel of that mini train? You are given 30 centimeter, convert it into meter, 30 upon 100, 0.3 meter, time is given to you 10 seconds, okay. Simplify, answer is minus 1.667, and you must be remembering the unit of angular acceleration, radian per second square, radian per second square. Tell me, what does this negative sign indicate? It indicates that as time passes on, the angular velocity goes on decreasing. That is why the angular acceleration value mathematically comes out to be negative. In physics, we call it angular deceleration or angular retardation, or angular deceleration. Got it? Now, read the statement of sum number 3. Come on, read it. Recall third equation of rotational motion with constant angular acceleration. What was that? Omega square minus omega 0 square equals to 2 alpha theta. Omega square minus omega 0 square equals to 2 alpha theta. Correct? Now, this final angular velocity must be 0. because here you are given truck, and truck also stops after finishing certain number of rotations. Because the truck is getting stopped, final angular velocity must have become 0. What is the value of omega 0 from here? Omega 0 is V0 upon R. Omega 0 is V0 upon R, square of it, and that equals to 2 alpha theta. Now this part is 0, minus as it is. What is V0? Initial velocity, and that initial velocity you are given, come on, 54 kilometer per hour. No, it will not do. You must transfer it into meter per second. Just now I told you, multiply by 5 divided by 18 divided by R. What is R? Radius of wheel of truck, which they are given 50 centimeter, converted into meter, 50 upon 100, 0.5 meter. Don't forget to make it squared. That equals to 2 into alpha as it is. What about theta? Theta is angular displacement. You are not given that angular displacement directly in radian. No, you are given, come on, 20 rotations. Now you must convert rotation into radian. One rotation means 2 pi radian. Always, whenever you require to convert number of rotations or number of revolutions into radian, you must multiply by 2 pi. So 20 rotations when converted into radian, you must multiply by 2 pi. And now simplify and find out value of alpha. Put value of pi equal to 3.14. Find out alpha. It comes out to be minus 3.58 unit of angular acceleration. Come on, radian per second square. Again here also alpha has come out to be negative. It shows decrease in angular velocity with respect to time. That is, it is angular deceleration. Okay. One more thing is asked to us. By the time the wheel of truck finishes 20 rotations, by the time what is the linear distance traveled by the truck? That is what we have to find out. I am showing you how to find it. Consider a road surface like this, horizontally. Here is the position of wheel at one point of time, and you just mark one point on the surface of the wheel. Fine. Suppose that point is this, and now push the truck ahead, correct? Let it move ahead, and such that when the truck is moving ahead, you will notice that this marked point moves on this periphery this way, and by the time once again it comes in the contact with the road surface, by the time the truck has traveled some linear distance in forward direction. That linear distance is this much. Come on, from here to here. Actually it is equal to this much, which is nothing but circumference of a circle having radius r. What is it? 2 pi r. So remember, whenever on a straight road, whenever any vehicle, wheel of any vehicle finishes one rotation, the linear distance traveled by the vehicle is 2 pi r. In one rotation, if this much linear distance is traveled, then naturally in n number of rotations, what would be total linear distance traveled? N into 2 pi r, correct? Right now number of rotations is given to you 20, 2 as it is, pi value is 3.14, radius is 50 centimeter, convert into meter, 50 upon 100, 0.5 meter. Simplify, answer is 62.8 meter. Okay, fine. Now my dears, we go for theoretical part once again. The topic which we are going to discuss now is of maximum importance in the whole of physics. It is about torque. You must understand this concept clearly. It will be used often and often in the later part of the chapter. Okay, try to understand what is called torque. Fine. Suppose you are given a cricket ball, okay, and you are asked to produce linear motion in that ball. What will you do? You will simply throw it, correct? While throwing it, what are you doing? You are exerting force on it. So force is that physical quantity which is responsible for producing linear motion in a body. Now suppose you are asked to rotate that ball, correct? Just keep it on the table surface and try to rotate it. So when you are making that ball rotating, at that time also you are exerting some sort of tangential force on the surface, and that tangential force produces that physical quantity which is responsible for rotational motion. That very physical quantity which is responsible for rotational motion is only known as torque. So torque is nothing but, you can say in other equivalent words, you can say torque is nothing but force of rotational motion. Force of rotational motion. Let me tell you, whatever role is played by force in linear motion, same role is played by torque in rotational motion. Whatever role is played by force in linear motion, same role is played by torque in rotational motion. Now let us study in detail what is actually torque. I am showing you. To understand the definition of torque, you please consider a rigid body of any arbitrary shape. Arbitrary shape means at random you can select any shape, might be regular, might be irregular, no problem. Here I have shown the shape very much like they have shown in the textbook. Now this is a rigid body. Actually here we have shown cross section of that rigid body taken parallel to the plane of the figure. Fine. Now what does this body do? It performs rotational motion, say anti-clockwise, when you view from front side about this axis, say z axis, which is perpendicular to plane of the figure. Fine. Now you just consider any one constituent particle of that rigid body, say particle Q. Fine. Now when this particle is performing circular motion, this is the center, and with respect to this center, position vector of this particle is suppose vector r. Now to produce this rotational motion, initially we must have exerted some force. Suppose that force was exerted on this particle, say in this direction. Say it is vector f, which makes angle theta with the direction of vector r. So angle between directions of vector r and vector f, at present I am taking theta. Fine. Do one thing, resolve this vector into two mutually perpendicular components. Come on, this vector plus this vector. This vector plus this vector will give you this vector. Correct? Come on, this vector plus this vector will give you this vector. So what are these two? Two mutually perpendicular components of this force vector. Now out of two components, let us find out that formula. Very simple. This is the component. Come on. Component of vector f adjacent to theta. What is it? F cos theta. Component of f opposite to theta. What is it? F sin theta. Adjacent to theta, f cos theta. Opposite to theta, f sin theta. Now just put this component from here to here. Just shift it from here to here. This is also f sin theta. You can see this I have written here, f sin theta. Now we would like to find out of these two components, which component is responsible for producing rotational motion in this rigid body. First of all, talk about this force. What is that? F cos theta. I say this component is not at all responsible for rotational motion because it is exerted parallel to vector r. It cannot produce any rotational motion. Then you may ask why? See the reason. Actually this force wants to shift this particle, wants to displace this particle away from this axis of rotation. But tell me, how is this body? This is a rigid body. In a rigid body, relative positions of various constituent particles remain invariant. So this particle is not going to displace. That is why I say that this force, though it is exerted, will not produce any effect. It is not responsible for rotational motion. Just discard it and now consider this component. Which one? F sin theta. How to find it? This component is come on perpendicular to vector r. You know what will it do? This component will produce rotational motion this way, and every point of time, at any moment, it will keep this particle exactly distance r away from axis of rotation. So there is no deformation and yet rotational motion is produced. So the component which is responsible for producing rotational motion is F sin theta, which is perpendicular to vector r. Okay. Now see, practically what do we find? Effectiveness of external force in producing rotational motion would increase if the point of application of force is at greater distance from axis of rotation. If the value of modulus of vector r or distance of this particle from this axis is more, then effectiveness of this force exerted in producing rotational motion is also more. That is why I have written here, effectiveness of force is directly proportional to r, where r is the distance of point of application of force from axis of rotation. Not only that, as this perpendicular force increases, then also the effectiveness of force increases. So effectiveness of force is directly proportional to F sin theta. Either of these two or both of them are increasing, then we find that amount of rotational motion also is more. So effectiveness of force which is applied to produce rotational motion would increase when this multiplication increases. Come on, take the multiplication just to have combined dependence. Take the multiplication r into F sin theta. So effectiveness of force is now resultantly, as a final result, as a you can say combined result, it is now directly proportional to multiplication of these two. Take the multiplication r into F sin theta, r into F sin theta. Now tell me, earlier how much will be the linear motion produced in the cricket ball? That was dependent only on force. But how much is the rotational motion produced in a given body? That is not only depending on force, along with the force it also depends on r, it also depends on theta, that is angle between vector r and vector f. Altogether it depends on this combined physical quantity, that very combined physical quantity on which amount of rotational motion depends, or on which effectiveness of force applied for producing rotational motion depends. That combined physical quantity itself is known as torque, and it is shown by specific symbol like this to be pronounced as tau. TAU is its spelling, TAU to be pronounced as tau. So this combined physical quantity which is responsible for rotational motion is only defined now by the word, come on, new name is torque, and the symbol is this. Come on, this is taken as torque, shown by symbol tau. Tau equals to Rf sin theta. Tau equals to Rf sin theta. Wait. Take this tau as magnitude of vector tau. Magnitude of vector tau. You can take it because it is a vector quantity. And if it is AB sin theta, you have studied in first semester. If it is AB sin theta, it can be taken as modulus of vector A cross vector B. Similarly, here it is Rf sin theta. I can take it as modulus of vector R cross vector F. And now just delete the sign of modulus from both the sides. Remove the sign of modulus, then you will get it here vector tau. Here you will get vector R cross vector F. So basically torque vector is nothing but a cross product between position vector and force vector. Okay. This is just an introduction. Later on we are going to define what is called torque. Okay. So tell me the conclusion of whole discussion. After all, what is torque? It is a quantity which is responsible for producing rotational motion in a body, and that quantity from formula point of view is tau equals to Rf sin theta, correct? It gives you measure of effectiveness of applied force in producing rotational motion. If torque is more amount of rotational motion is produced. If torque is less amount of rotational motion is produced, correct? Fine. Now let us take different points regarding this torque. First, torque exerted on a single particle. Torque exerted on a single particle. As usual, let us take this right hand side axis as x axis, vertically upward axis y axis, and this axis which is coming out of the plane of the figure perpendicularly, it is z axis. Fine. Now think of xz plane. Think of xz plane. If this one is x axis, this one is z axis, then plane passing through x and z axis, it is this horizontal plane. This horizontal plane. Okay, fine. Now, in this xz plane, you just consider a particle, correct? Say particle q. Its position vector with respect to origin is this vector, correct? Vector OQ, and that vector is vector R, correct? Now suppose force exerted on this particle is in this direction, which is lying in the same xz plane. Okay, fine. That force is vector F. This is the direction of vector R. This is the direction of vector F, and hence this much is the angle between them. Fine. Now tell me, this is vector R, that is position vector. This is vector F, that is force vector, and you know what is called torque. It is vector product between position vector and force vector. So taking this equation in consideration, you can define now what is called torque exerted on a single particle. Very simple. If vector R is the position vector of a given particle with respect to given reference point, and if vector F is force exerted on it, then a vector product, which vector product? Vector R cross vector F is called torque exerted on that particle with respect to that reference point. Once again, if vector R is the position vector of a given particle with respect to given reference point, and if vector F is force exerted on it, then a vector product, vector R cross vector F, is called torque exerted on that particle with respect to that reference point. Got it? Fine. Now let us find out direction of vector tau. Direction of vector tau. You should simply find out direction of vector R cross vector F. Now tell me, take this as vector F and take this as vector R. Come on. Take this as vector R, take this as vector F. So situation is like this. This is vector R, this is vector F. How I am showing you? Actually this is vector F, correct? But what I have done, I have shifted that vector from here to here, correct? Because you know, for finding direction of a vector product, first of all you should place both the vectors on each other such that they should have a common tail. Right now, tail of this vector is here and tail of this vector is here. Both of them are not present at the same point. No. So what you should do? You should shift this vector from here to here without changing its magnitude and direction. And now you can see tail of this vector is also here, tail of this vector is also here. Now situation is like this. Say this is vector r, which is this, and say this is vector f. Okay, vector r, vector f, vector r, vector f. Correct. Now think of a plane passing through these two vectors. That plane passing through these two vectors, it is this xz plane, which is right now horizontal plane. And now think of a right-handed screw which is perpendicular to that plane. Correct. Think of this right-handed screw this way. And now rotate this screw in a manner first vector rotates towards second vector. First vector is vector r, second vector is vector f. I should rotate vector r towards vector f through the angle between them this way. This is vector r, this is vector f. I should rotate this vector towards this vector this way. And in the same manner, I should rotate this right-handed screw also. And if I rotate this right-handed screw in the same manner this way, then it will advance vertically upwards. And that direction of advancement of right-handed screw, which is right now vertically upwards, should be taken as direction of this vector product. That is, should be taken as direction of vector tau. That is why here I have written vector tau, and vector tau is nothing but vector r cross vector f. At present, it comes out to be along, say, y-axis, which is perpendicular to xz plane. Now situation is this. Look, this is vector f, this is vector r, and vector tau is like this. Correct. Now tell me, how to find this vector? It is at right angle to this vector. This angle is 90 degree. Correct. And angle between this and this is also 90 degree. Correct. You can see in the diagram, vector tau is perpendicular to vector r as well as perpendicular to vector f also. This direction is perpendicular to vector r. Look, this is the right angle, correct? And this direction is also perpendicular to this vector f. This is also right angle. Just to show that angle is exactly right angle, what you should take care? Parallel to this is this line segment. Parallel to this is this line segment. Similarly, parallel to this is this line segment. Parallel to this is this line segment. Correct? And then only you will find them as right angles. Okay? Fine. Now what about unit of torque? Let us find out unit. Unit of force is Newton. Unit of distance is meter. You know, sin theta, cos theta, tan theta, they are all trigonometric functions having only numerical values, having no unit. So don't bother for the unit of this part. Come on, unit of force is Newton. Unit of distance is meter. Now unit of torque has come out to be Newton into meter. In MCAS, in CGS, instead of Newton you may write dyne, instead of meter you may write centimeter. Okay. What about dimensional formula of torque? Come on, write down dimensional formula for force and length. For force, don't you know? Dimensional formula of force, m raised to 1, l raised to 1, t raised to minus 2. Multiply by dimensional formula for length, it is l raised to 1, correct? Just multiply m raised to 1, l raised to 1 plus 1, that is 2, t raised to minus 2. Can you recall? Work also has same dimensional formula, and unit of work is also Newton into meter. Though unit and dimensional formula for both work as well as torque are same, then also these quantities are not same quantities. Torque and work are not identical physical quantities. There is a very big difference between them. Torque is a vector, work is a scalar. Torque is a vector, work is a scalar. Okay, fine. Let us think when the value of torque would be 0, when tau equals to 0. Let us think. Look in this formula. When this torque will be 0, either r equals to 0 or f equals to 0 or sin theta equals to 0, naturally tau will be 0. Either r equals to 0 or f equals to 0 or sin theta equals to 0, then come on, tau will be 0. But tell me when sin theta will be 0. When sin theta will be 0. provided this theta is either 0 degree or 180 degree. At that time sin theta will be 0. But tell me now when theta will be 0 degree and when theta will be 180 degree. I am showing you. What is theta? Angle between vector r and vector f. And when it will be 0 or 180 degree, I am showing you. Instead of taking reference point here, suppose we are taking reference point here, correct? Then with respect to this reference point, what is the position vector of this particle? It will be this way, correct? This way. And this way means what? In the same direction as that of force. So at that time vector r and vector f, they both will be in the same direction. So theta will be 0 degree. And suppose you are selecting reference point over here, then with respect to this reference point, what is the position vector of this particle? It will be this way, correct? And vector f is this way. This is vector r, this is vector f. Vector r, vector f, vector r, vector f, they are in opposite directions. So angle between them will be 180 degree. Fine. Now tell me, what is this line? This is the line on which, come on, the direction of force is located. Such a line along which direction of force is aligned is known as line of action of force. Line of action of force. So if you take reference point here or here, means you are taking point on the line of action of force. If you are taking reference point on the line of action of force, then theta is either 0 degree or 180 degree. In both the cases, sin theta would be 0 and ultimately torque will be 0. So even if r is not 0, even if f is not 0, if you select reference point on the line of action of force, then theta is either 0 degree or 180 degree. In both the cases, sin theta would be 0 and torque will be 0. Correct? Now, mention of reference point is a must while giving definition of torque, because if you do not specify the reference point, then there is no meaning of mentioning the value of torque, because as soon as you will change this reference point, then the distance of given particle from new reference point, the distance r would change and angle theta also would change. If either r or theta or both of them are changing, then this product will change, torque will change. So whenever you mention torque value, you must say with respect to which reference point this much is the torque. That reference point must be mentioned along with the mention of torque. Okay, reference point must be mentioned while mentioning torque. Okay, fine. Now remember, 4 points are not necessary. Which 4 points are not necessary? I am showing you one by one. First point, see, it is not necessary that considered particle must be of a rigid body, not necessary. Second, not necessary that this particle should lie in the XZ plane only, should lie in the horizontal plane only, not necessary. Third point, not necessary that force should be exerted on that particle in the direction which is in the horizontal plane, not necessary. And fourth point, it is not necessary to take every time origin as a reference point, not necessary. You may take any other point as the reference point. I repeat, not necessary that considered particle must be of a rigid body. Not necessary that direction of position vector, vector r, should lie in the horizontal plane, not necessary. Third, not necessary that vector f should lie in the horizontal plane, not necessary. And fourth point, it is not necessary to take origin every time as a reference point, not necessary. Got it? Now let us prove one result. Prove that torque is equal to moment of force. Torque equals to moment of force. First of all, tell me what is called moment of force. Moment of force is nothing but product of magnitude of force and perpendicular distance of line of action of that force from some reference point. Such a product is called moment of force, and that moment of force we have to prove to be equal to torque. How to prove? Very simple. Tell me. Just extend this vector f in backward direction. This will give you line of action of force. Line of action of force. Fine. Let me write here line of action of force. So this line is line of action of force. Line of action of force. Line of action of force. Fine. Now tell me, if this angle is theta, naturally this also will be theta, vertically opposite. Now just draw one perpendicular from reference point onto this line of action of force. When you draw perpendicular, this is the foot of perpendicular. So now this will give you perpendicular distance of this reference point from this line of action of force. And how much is the distance OM? Distance OM would be component of R opposite to theta. Component of vector R opposite to theta. What is it? R sin theta. So this component is R sin theta. Now tell me, what is the magnitude of torque? RF sin theta. Magnitude of torque is RF sin theta. Can you rewrite this way? F into R sin theta. Yes, we can write F into R sin theta. But what is F? F is force, magnitude of force. And what is R sin theta? What is this much distance? Perpendicular distance. Perpendicular distance of reference point from line of action of force. Perpendicular distance of reference point from line of action of force. It is OM, correct? Which is R sin theta. So R sin theta is nothing but perpendicular distance. And I told you, product of magnitude of force and the perpendicular distance of line of action of force from some reference point, such a product is called moment of force. So ultimately what we have proved? Torque equals to moment of force. Torque equals to moment of force. Now my dears, let us prove one more important result. Resultant torque is found to be equal to moment of a couple. Then you may have a question, what is called a couple? See, couple is consisting of a pair of forces which are equal in magnitude, opposite in direction, and which are not collinear. A pair of two non-collinear forces with equal magnitudes and opposite directions constitute a couple. Again, a pair of two non-collinear forces having equal magnitudes and opposite directions is called a couple, correct? And we find that resultant torque is equal to moment of a couple. Fine. Come on. Let us prove resultant torque equals to moment of a couple. As shown in the diagram, you just consider two particles, correct? Say particle number 1, particle number 2. Position vector of particle number 1 with respect to origin is vector r1. Position vector of particle 2 with respect to origin is vector r2. Fine. Join second particle with a first particle by such a vector. Okay, fine. Now that vector will be vector r1 minus vector r2. How? See, when you are going from here to here, what are you doing? You are making displacement, and displacement vector is always final position vector minus initial position vector. What is, when you go from here to here, this is final point. So what is final position vector? Vector r1 minus, you started from here, so this was initial point. So what is initial position vector? Vector r2 minus vector r2. Final position vector minus initial position vector will give you displacement vector. Fine. Now tell me, if you want this much length, you should take magnitude of this vector, correct? Fine. Now, on this particle number 1, suppose force is exerted in this vertically upward direction with magnitude say F1, and on this second particle, come on, force is exerted in vertically downward direction with magnitude say F2. Suppose we take these two magnitudes equal, that is F1 equals to F2. Mind well, magnitudes are equal, but directions are not same. This direction is vertically upwards, this direction is vertically downwards. In short, they are opposite in directions and they are non-linear. They are non-linear, means their lines of action of forces do not coincide on the same line. Okay, they are non-linear forces. Non-collinear. If the lines of action superpose on the same line, we say they are collinear, and these forces are not among them. These are non-collinear forces. Non-collinear forces. Got it? Fine. Now tell me, this is the line of action of this force, correct? That is vector F1. This is line of action of vector F2. This much is the perpendicular distance between these two lines of forces. Perpendicular distance is this much. Let us find out that distance. Just consider this angle as theta, correct? And now, how much is this? It is component of this opposite to theta. Come on. Component of this opposite to theta. So it would be mod of vector r1 minus vector r2 sin theta. Mod of vector r1 minus vector r2 into sin theta. This much is the perpendicular distance between the lines of actions of vector f1 and vector f2. Fine. And now just remember one thing, as many forces, that many torques. As many forces, that many torques. Two forces, then two torques. Let them be vector τ1 and vector τ2. If you want resultant torque, you must make vector addition of these two torques. What is vector τ1 from basic definition? Vector τ1 you can find out from here. It will be vector r1 cross vector f1. Here it is, vector r1 cross vector f1. Plus, what is vector τ2? It is vector r2 cross vector f2. Fine. Now this vector r1 cross vector f1 as it is, vector r2 as it is, but instead of vector f2 I am putting minus of vector f1, because these two forces are negative vectors of each other. You know from first semester, if vector f1 and vector f2 are negative vectors of each other, then vector f2 can be replaced by minus of vector f1. Vector f2 can be replaced by minus of vector f1, correct? Now, vector r1 minus vector r2, that much part I am putting in a bracket, cross vector f1, cross vector f1, this much part I just take out, okay, fine. Now, this is a vector product between these two vectors, and you know, if it is vector A cross vector B, what is its magnitude? AB sin theta. AB sin theta, that is magnitude of first vector multiplied by magnitude of second vector multiplied by sine value of angle between them. Magnitude of this I have written here. Magnitude of this I have written here. Multiplied by sine of angle between them. Angle between this and this, it is pi minus theta. How? Look in the figure. This angle is theta, correct? And between these two, total angle is pi radian, correct? Out of pi, you just subtract this theta, so remaining angle is pi minus theta. This is the direction of vector r1 minus vector r2, this one, and this is the direction of vector f1. So angle between vector r1 minus vector r2 and vector f1 is at present pi minus theta. So angle between this vector and this vector, it is pi minus theta, correct? Now this part as it is, magnitude of vector f1 will give you only f1, and sine of pi minus theta, it is as good as, come on, sine theta. Now this f1 I have written into modulus of vector r1 minus vector r2 into sine theta. Tell me what is f1? What is f1? Magnitude of first vector. Magnitude of first vector. You may take magnitude of this or magnitude of this, no problem, because both the magnitudes are equal. So you can say magnitude of either of two forces which are non-collinear and which constitute couple. Okay. So magnitude of either of two forces, come on, multiplied by modulus of vector r1 minus vector r2 into sine theta. Tell me, f1 is magnitude of either force, and how much is this? Come on, this part gives me what? This part gives me what? Perpendicular distance between the lines of action of two forces. Come on, this much part would give me perpendicular distance, and you know, product of force and perpendicular distance of line of action of force from some reference point is going to give you moment of that force. But here there was not a single force, there were two forces. So we call this product as moment of a couple. Moment of a couple. Earlier what we had proved, that torque is equal to moment of force, and now we are proving that resultant torque is equal to moment of a couple. Simply torque is equal to moment of force, and if it is resultant torque, then it is equal to moment of a couple. I repeat, what is called a couple? A pair of two forces having equal magnitudes, opposite directions, and which are not linear, correct? Which are not collinear, means there should be some perpendicular distance between them, okay? They should not be, the lines of action should not be on the same line. There must be some perpendicular distance between the lines of action, then such a pair of forces will constitute what is called couple. Now we go for resultant torque exerted on a system of particles. What is called resultant torque exerted on a system of particles? Consider a system of n number of particles in which torque exerted on first particle is vector tau1, torque exerted on second particle is vector tau2, torque exerted on last particle is vector tau n. And then remember, all these torques we have found out with the same reference point, with respect to same reference point. And then if you make their vector addition, then that vector addition is called resultant torque exerted on that entire system. How would you define it? Very simple. Vector addition of torques exerted on all the constituent particles of a given system with respect to a given reference point is called resultant torque exerted on that whole system with respect to that reference point. I repeat, vector addition of torques exerted on all the constituent particles of a given system with respect to a given reference point is called resultant torque exerted on that whole system with respect to that reference point. Fine. Now this vector tau as it is, what is vector tau1? Torque exerted on first particle. From basic definition, vector r1 cross vector f1. Vector tau2 will be vector r2 cross vector f2 plus dash 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 plus vector tau n is equal to vector rn cross vector fn. Fine. Now tell me, all these terms, they can be represented by a single term. See, after all, you are doing the addition of which sort of term? Term like Position vector cross product with force vector. Position vector cross product with force vector. The way you are taking that product for first particle, here for second particle, here for last particle, here I am taking for ith particle, correct? Where I, which is suffix, indicates order of particle, that you should change from first to last. That's why instead of this whole summation, I just put a single term, vector Ri cross vector Fi, and because I am supposed to take their algebraic addition, I am just putting symbol sigma. It means to say addition of such terms in which I indicates the order of particle, which you must change from first to last. That is why I am putting I equal to 1 to n. Okay. This is how you can find out resultant torque exerted on whole system. And now we define what is called torque exerted on a rigid body. Fine. Consider this as a rigid body which at present performs rotational motion about, say, this stationary axis of rotation, say z axis. Not necessary that you should take these axes as z axis only, not necessary, but we just go according to textbook. Fine. In textbook they have taken these as x axis, this one as y axis, this as origin. Now just consider any one of the constituent particles, say particle q, and then position vector of this particle with respect to origin is vector Rn. And suppose force exerted on this particle is vector Fn. Then don't you know torque exerted on this particle according to vector relationship? Come on, vector tau n equals to vector Rn cross vector Fn. Come on. This much is the torque exerted on nth particle which is considered at present. This nth particle may be any order of particle. Here the order of particle in textbook they are shown by symbol n. That also should be changed from first to last. At present we are considering only one of the constituent particles. Fine. Vector tau n as it is. Okay. And now what is vector A cross vector B formula in terms of 3 by 3 determinant which you had studied in semester 1? Remembered? Vector A cross vector B, it was equal to 3 by 3 determinant, I hat, J hat, K hat, AX, AY, AZ, BX, BY, BZ. Similarly here, come on, 3 by 3 determinant, I hat, J hat, K hat, then position vector is vector Rn, its 3 coordinates we are going to write, its 3 components we are going to write this way, xn, yn, zn. What about components of this vector now? fnx, fny, fnz. What is this? X component of force exerted on nth particle, y component of force exerted on nth particle, z component of force exerted on nth particle. Okay, fine. Now you may wonder, actually we want, come on, the torque exerted on entire rigid body, then why we are finding torque exerted on a single particle? The reason is that whenever you exert torque only on one of the constituent particles of a rigid body, it simply does not produce rotational motion in that particular particle, but along with that particle it produces rotational motion in the entire rigid body, as if you are exerting torques on all the constituent particles. To open the door or to close the door, do you exert torque on each and every particle of the door? No. We just exert torque only on the handle, and that produces rotational motion in the entire door. So I mean to say, torque exerted on a single particle becomes equal to torque exerted on the entire rigid body. That's why we are finding, come on, this torque exerted on one particle, say nth particle. Okay, fine. Now tell me, expand this now. You know how to expand this. First of all, consider I hat, and you should cancel this column and this row, and with I hat what will be the part in multiplication? This into this minus this into this. So come on, with I hat in multiplication you will get yn into fnz minus zn into fny. Yn into fnz minus zn into fny into I hat. And as such, in semester 1, we were writing here minus j hat. Remembered? Cancel this column, cancel this row. With minus z, you are writing in multiplication this into this minus this into this, correct? But here I want to write with plus z. If you want to write with plus z, then the multiplier will be this into this minus this into this. Come on, this into this, Zn into Fnx, Zn into Fnx minus Xn into Fnz minus Xn into Fnz, correct? And with that multiplied is with plus j hat. And with plus k hat, cancel this column, cancel this row. With plus k hat, what will be the part in multiplication? Come on, Xn into Fny minus Yn into Fnx. Xn into Fny minus Yn into Fnx. This into k hat. Fine. Now this much is the torque exerted on a single particle, correct? Now you should add all such torques for all the constituent particles of a given rigid body containing n number of particles. That's why we are making vector addition of such torques, sigma of vector tau n, where n indicates order of particle which you must change from 1 to n, first to last. And then you will get, come on, torque exerted on whole rigid body, correct? But out of this torque, which component is at present responsible for producing rotational motion? I am showing you. Right now, stationary axis of rotation is z axis, correct? So whatever torque expression you get from here, its a z component is responsible for producing rotational motion, because axis of rotation is at present z axis. That is what I have written here. Look, component of torque responsible for rotational motion about stationary axis of rotation is equal to component parallel to stationary axis of rotation. Here stationary axis of rotation is z axis. So right now z component of this torque is responsible for producing rotational motion. Similarly, if x axis is taken as axis of rotation, then x component of this torque is responsible for producing rotational motion, and if y axis is taken as stationary axis of rotation, then y component of this torque is responsible for rotational motion. But not necessary that every time torque should be either along x axis or y axis or along z axis, not necessary. Suppose torque exerted on the whole rigid body comes out to be in this direction, correct? Say in this direction vector tau, and this is the stationary axis of rotation. And now define one unit vector along this stationary axis of rotation, let it be n hat. Now angle between vector tau and this n hat is suppose theta. If torque exerted on a rigid body is not parallel to its stationary axis of rotation, then you should take that component of this torque which is parallel to axis of rotation, and for that you can just find out component of tau adjacent to theta, which is tau cos theta. So in that case, this tau cos theta is responsible for producing rotational motion of this rigid body about this stationary axis of rotation. In semester 1, remember, when the block was lying on the horizontal surface and vector F was exerted in this direction, and this angle made by that force vector with the horizontal surface was theta, at the time which component of force was responsible for producing linear motion? It was component of F adjacent to theta. What was that? F cos theta. So in case of linear motion, that component of force which is parallel to linear axis becomes responsible for producing linear motion. Similarly here, that component torque which is parallel to axis of rotation becomes responsible for producing rotational motion, and that component is nothing but tau cos theta, or you may write it this way, vector tau dot n hat, vector tau dot n hat. How? Don't you know vector A dot vector B equals to AB cos theta? Meaning thereby inverse magnitude of first vector multiplied by magnitude of second vector multiplied by cos theta. magnitude of first vector is tau, magnitude of second vector, because it is unit vector, magnitude is 1 into cos theta. So what is this? Tau into 1 into cos theta means it is tau cos theta. Tau cos theta, correct? Fine. Come on my dears, let us today understand about what is called equilibrium condition of a rigid body. Say a rigid body can have two types of equilibriums. Which two types? One is called linear equilibrium, another is called rotational equilibrium. Let us see one by one. When a rigid body is said to be under linear equilibrium, very simple. Whenever resultant force exerted on a given rigid body is 0, it is said to be under linear equilibrium. But whenever resultant force is 0, it means to say vector addition of all the forces exerted on that rigid body must come out to be 0 vector. And whenever any vector is a 0 vector, then its all the three mutually perpendicular components must be 0 at a time. So algebraic summation of x components of all the forces must be 0. Algebraic summation of y components of all the forces must be 0. Algebraic summation of z components of all the forces must be 0. If these conditions are satisfied, then rigid body is said to be under linear equilibrium. Now let us see when the rigid body is said to be under rotational equilibrium. Very simple. Whenever resultant torque exerted on the rigid body is 0, it is said to be under rotational equilibrium. When resultant torque is 0, naturally vector addition of all the torques must be 0 vector. And you know from first semester, whenever any vector is 0 vector, its all the three mutually perpendicular components must be 0. So algebraic summation of x components of all the torques must be 0. Algebraic summation of y components of all the torques must be 0. Algebraic summation of z components of all the torques must be 0. Correct? Fine. Now please read this statement of illustration number 5. It is a very good example. Come on, read the statement. Tell me, what is given to us? On a horizontal surface, there lies a block of mass small m. Correct? At this right hand side top corner, we have exerted external force, say by magnitude capital F at an angle theta with the horizontal direction. And by exerting that force, they have said in the statement that this block starts sliding towards the right hand side with a constant velocity. If this is the situation, then what is the perpendicular distance of line of action of normal force exerted on the block from this reference point O? That is what we have to find out. Come on, let us find out this way. On a body of mass m, everybody knows there is downward gravitational force which is mg. It is always exerted at a midpoint. Better you say centroid, and better you say center of gravity. So exactly on this center of gravity, there will be gravitational force or weight of the block, and it is vertically downwards by magnitude m into g. Fine. Now this total length they are given as L. Because this is the center of gravity, it is exactly at the centroid. which is at half of the length. So this much distance is half of capital L. So I am writing here L by 2. Okay, fine. Now this is the force exerted by the block on this stable surface vertically downwards in the form of force of action. Then this stable surface will now provide opposite force of reaction. But because this force of reaction is provided onto this block in a direction perpendicular to contact surface, we call it normal force. Perpendicular force of reaction is called normal force, shown by symbol capital N. Here the line of action of this normal force is at perpendicular distance x from this reference point. Then you may have a question that why it is not getting exerted here, correct? And why it is shifting toward the right hand side. The reason is that this force you are just exerting on the right hand side part, that is why. If you are not exerting the force, we will prove that this normal force will be exerted here only, correct? And by chance if you exert this external force on the left side here, then this line of action will be shifting on the left side. Okay, right now towards right hand side, because this force is towards right side, that is why. Now just resolve this vector into two mutually perpendicular components. One is f cos theta, another is f sin theta. Adjacent to theta is cos component, opposite to theta is sin component. So adjacent to theta it is f cos theta, opposite to theta here you can consider f sin theta. But this component I have shown here, correct, f sin theta. Once you resolve any vector into two mutually perpendicular components, then after you should forget about that vector and you should concentrate only on the mutually perpendicular components. So now forget about f, you think of f cos theta and f sin theta. This height they are given as h. Now tell me, this block is lying under linear equilibrium because it is moving toward the right hand side with constant velocity. For linear equilibrium, you know, whatever is the force towards right side, same must be force towards left side. What is the force exerted on this block towards right side? It is only one force, it is f cos theta. And that should be exactly getting balanced by left hand side force. If block is moving towards the right hand side, then in just opposite direction there will be force of friction. Because block is in motion, this frictional force is kinetic frictional force, which is towards left side. So when this block is under linear equilibrium along x-axis, whatever is the force towards positive x-axis, same must be force towards negative x-axis. This is the force towards positive x-axis, this is the force towards negative x-axis, both of them must have equal magnitude. So f cos theta must be equal to fk, f cos theta must be equal to fk. This block is also under linear equilibrium along y-axis. So whatever is upward force, same must be downward force. Whatever is vertically upward force, same must be vertically downward force. There are two vertically upward forces, one is capital N and another is this force which is f sin theta. Just make the addition n plus f sin theta. That should be equal to vertically downward force, that is mg. Vertically upward force should be equal to vertically downward force. Find out n, transfer this. So it is mg minus f sin theta, mg minus f sin theta. Give it equation number 2. Fine. And now, during the motion, this block does not rotate. So it is also under rotational equilibrium. And if any block or any body is under rotational equilibrium, then algebraic summation of all the torques must come out to be 0. Let us do one thing. Whichever torque is giving this block clockwise rotation according to textbook, let us take them as negative, and any torque giving anti-clockwise rotation, let us take according to textbook as positive. Torque giving clockwise rotation should be treated negative. Torque giving anti-clockwise rotation should be taken positive. Let us take one by one. As many forces, that many torques. And you know torque formula, tau equals to Rf sin theta. that is F into r sin theta. F into r sin theta means force into perpendicular distance. Force into perpendicular distance. Let us start with this. First force I am taking this one, Fk. Force into perpendicular distance. Perpendicular distance of line of action of this force from this reference point is 0, because this reference point O lies on the same line of action of this force. So perpendicular distance is 0. Now talk about this force. Come on, force magnitude is mg multiplied by, come on, perpendicular distance of line of action of this force from this reference point O. It is this much. This much means, come on, this much, which is L by 2. But why I am taking it negative? Simple. With respect to this reference point, what is the position vector of point of action of this force? That position vector will be like this, correct? So this is vector R. Something like this. Look, this is vector R and this is force vector, that is mg right now, correct? So this is position vector, vector R, this is mg. Both of them must be placed on each other such that they have a common tail. And now rotate R towards F. Rotate R towards F through the angle between them, correct? Come on, this way. And when you rotate it this way, correct, through the smaller angle between them, this outer angle is bigger angle, inner angle is smaller angle. Through the inner smaller angle, when you rotate R towards F, this rotation, manner of rotation is, come on, clockwise. That's why it is taken negative. Then talk about normal force. For this normal force, point of action of force is this. With respect to this reference point, the position vector of this point will be like this, correct? And this is force vector. And now shift this force vector from here to here. Come on, this is position vector. This normal force is exerted this way. Shift it from here to here, because we want their tails to superpose, correct? Here we want their tails to be coinciding at the same point. This is vector R, this is normal force, and now this is the smaller angle between them. Rotate R towards F this way, correct? When you rotate this way, the manner of rotation is, come on, anti-clockwise, then it should be taken positive. That's why I am putting plus sign, correct? And what about torque formula? Force multiplied by perpendicular distance. Force is N, and perpendicular distance of this line of action of this force from this reference point is this much or x. Okay, fine. Talk about this force now, F sin theta. Come on. Point of action of this force is this, and with respect to this reference point, the position vector of this point will be like this. This is vector R. And now this is vector R. This is F sin theta. Just put it from here to here. This is vector R. This is F sin theta. Now rotate R towards F through the minimum angle between them, smaller angle between them. Come on, rotate R towards F through the smaller angle between them this way. Manner of rotation is anti-clockwise, that's why positive. And what is the torque formula? Force multiplied by perpendicular distance. Force is F sin theta. Perpendicular distance of line of this force from this reference point is this much, or it is L. Now last term, talk about this force. Point of action of this force is this. With respect to this reference point, the position vector of this very point is this, vector R, and F cos theta is this way. Something like this. This is vector R, F cos theta is this. Just put it here, such that they have a common tail. Now this is position vector, this is force vector. Rotate vector R towards vector F through the smaller angle between them this way. And when you rotate this way, the manner of rotation is clockwise. That's why it should be taken negative. That's why I am putting here negative sign. What is the torque magnitude? It is force multiplied by perpendicular distance. Force is this right now. How much? F cos theta. Multiplied by perpendicular distance of line of action of this force from this reference point will be this much, or it is H. That's why I am putting here H. Fine. And now tell me, this part is 0, correct? I want n into x. So make it subject of the equation. This term I just transfer it on right hand side. From minus it will become plus. Plus mg into L by 2. This term is right now minus. Transfer it on right hand side will become plus f cos theta into h. This term right now plus. If I transfer it on right hand side will become minus f sin theta into L. I want only x. Put n down. Okay. So all these terms in the numerator I have written as it is, no change whatsoever, and this n will come down. What will come down in the denominator? N, capital N. And capital N is this much, mg minus f sin theta. Capital N is mg minus f sin theta. Capital N is mg minus f sin theta. Now let us take that possibility. Suppose we do not exert any external force. Suppose. So if we do not exert any external force, then we will prove that line of action of this normal force will be same as that of weight. I am proving. When you do not exert any external force, F will be 0. Capital F is 0. When capital F is 0, this term will be 0. When F is 0, this term will be 0. When F is 0, this term will be 0. Now mg will cancel, giving you x equal to L by 2. X equal to L by 2. When x is L by 2, this x distance will be equal to L by 2, meaning that by this normal force will be exerted in upward direction passing through this center of gravity, correct, this way. And if it is getting exerted this way, then this distance x will be equal to L by 2. And similarly in the examination, they may give you this force not towards the right hand side, they may give you toward left side. In that case, this x will be less than L by 2. Right now x is, look in the figure, x is greater than L by 2. If no external force is there, x equals to L by 2. And if this force is exerted towards left side this way, then this normal force will shift on this side, then x will be less than L by 2. Got it?